Good morning. Today's lesson is on electrochemistry. By definition, electrochemistry is the relation of the flow of electric current to chemical changes. The relation of the flow of electric current to chemical changes. In previous lessons, we had alluded to the fact that there are two possibilities that we can have for this relationship. We could have either the chemical changes resulting in electric current, or electric current being the cause of the chemical changes. Let's write those two scenarios down. If we have the chemical change, which, remember, is a reaction, producing electricity, that would be one that is spontaneous in nature. If we had the reverse circumstance, where electricity is needed, to initiate the chemical reaction or change, that is non-spontaneous. Humans are interfering and forcing the situation. Nature does not want that to happen naturally. So these two scenarios, the spontaneous or the non-spontaneous situation, are representing two different electrochemical cells. Electrochemical cells are these electrochemistry concepts where, again, we're relating electric current to chemical changes. In today's lecture, we're going to introduce ourselves to both types of cells, talk about the components that they have in similarity, and then we're only going to focus in detail on one of the two. The lecture will be finished in the next lesson, where we focus on the second type of electrochemical cells. But again, we're going to introduce ourselves to both of them in today's lesson and then focus on the details of one. But before we get to the details of the cells, we need to elaborate a little bit more on how we know whether or not the reactions will be spontaneous or not. And that comes about by calculating cell potential. Calculating cell potential, which is symbolized E cell. Now, when you think back to your physics class, you saw this cell potential as voltage or electromotive force. Those were the units you were using in physics to talk about the number of electrons that are passing through the cell. But here in chemistry, we're going to focus on this, we call it cell potential because we're trying to talk about the chemical reactions themselves. In order for us to know whether we're going to have a spontaneous or a non-spontaneous reaction, when we do the math, our cell potential has to be positive. It has to be greater than 0 for a spontaneous reaction. The cell potential is measured at a specific temperature, 298 Kelvin. Remember, that's standard for chemical reactions. That's the same thing as 25 degrees Celsius. And again, all the other components will need to be in their standard states. The mathematical formula we'll use to calculate cell potential is the one here in the box. Our cell potential will equal the cell potential of the cathode plus the cell potential of the anode. The little degree sign here is meant to imply standard state, so we know what the temperature and the pressure at which the reaction is taking place at. And yes, the vocab words cathode and anode are new to us as of this moment in time. They will be defined more clearly in a few slides from now. So for the time being, let's just copy down the formula. The standard cell potential is equal to the standard cell potential of the cathode plus the standard cell potential of the anode. Now, where do we get these standard cell potential values from? It comes from our reference packet. What we're looking for in the reference packet, excuse me, we're looking for the standard electrode potential chart. So I'm going to get my yellow sheet and I'm going to flip through it, and it is reference packet table D, delta, or dog. And for those of you who are looking at it, you're saying, oh, we've used this before. We used this months ago to predict if single replacement reactions will work. So here's a little indication that single replacement reactions are actually redox reactions. If you remember, what we needed in the single replacement reaction was to make this backwards Z. Backwards Z. Sorry for my cramming of the letters here, but that's what we were using that chart for, to see if the single replacement reaction would work if we made that backwards Z. But what is actually going on is that we have one component of our single replacement reaction losing electrons and the other component of our chemical reaction gaining those lost electrons. So we have a redox reaction taking place. And the only way this will work is if naturally, again, we need this to be spontaneous, if the reaction will work naturally. So we need to make sure that the substance that most wants to be reduced is the one being reduced, and the substance that wants to be the most oxidized is the one, in fact, being oxidized. So while you're looking at that chart, I'm just going to scroll here. Right? Here's a colored version, perhaps, of what it is that we were looking at in Table D of our reference packet. And now let's get to the details. Now that we're knowledgeable about reduction-oxidation reactions, what is it that this chart is really trying to tell us? All right, the standard electrode potential charts. Again, cell potential is the voltage associated with a reduction reaction at an electrode when all solutes are 1 molar and all gases are at 1 atmosphere. So rephrasing that, every single reaction that you see on the standard reduction potential chart, they are all reduction. Leo the lion says GR. They're all gaining electrons. So when you look at these chemical reactions, all of the electrons show up on the reactant side of the reactions because they are all reduction reactions. But wait, I thought you can't have reduction without oxidation. You are 100% right. So that means that one component of these reactions as written will need to be reversed to represent oxidation. Okay, let's get back here. When we're reading these charts, hydrogen is used as our reference. In other words, its cell potential value is going to be 0 volts. If you're looking at it on your yellow sheet, you'll see that that's true, and you'll also see it here. It's highlighted for us in blue. Our standard value, everything that we're making a comparison to, is going to be compared to hydrogen. It's given this reference value of 0. So all of these positive and the negative values are all referencing or in comparison to hydrogen. And here's where the interpretation comes about. The more positive the cell voltage value, the more readily it is reduced. Let's say that again. The more positive the cell potential value, the more readily it is reduced. So looking at our chart, the more positive, so those are the numbers here, meaning they're above the line for the reaction for hydrogen. These are the ones that are most easily reduced, and I'll put them at the top. Most easily reduced. So fluorine, again, it's the most electronegative element that we have on our periodic table, is going to be the one that most easily gains electrons. So that's listed up here at the top. It has the highest or most positive cell potential value. It's the most easily reduced because this is a chart about standard reduction potentials. Getting back to our analysis here. Oxidation reactions require reversing the reaction. Oxidation reactions require reversing the reaction. So looking at our chart for a second, if the most easily reduced species are at the top of our chart because their values are the most positive, where do you suppose we'll see the substances that are most easily oxidized? That's right, they're going to be the ones that are the most negative in value, or the ones that are at the bottom of the chart. Most easily oxidized will be at the bottom. Most easily oxidized will be at the bottom. The generic concepts that we have here, again, the more positive value, and again, by value I mean the E cell value, will be reduced, and the more negative value and again, by value, we mean the cell potential value, E cell value, will be oxidized. I like to include this paragraph here that we just wrote down. The more positive E cell value will be reduced and the more negative E cell value will be oxidized, because it doesn't have to be. You're not locked in to having one positive and one negative value in your reactions. You might have two positive E cell values or maybe two negative E cell values. But again, the one that's more positive on this chart will be the one that's reduced, and the ones that more negative will be oxidized. So even if you do have that situation where you've got two positive E cells or two negative E cells, because oxidation reactions need to be reversed to show that these electrons are now lost, because remember, that's what Leo the lion means, right? Losing electrons, oxidation. The last thing we have in terms of our interpretation of this chart is that if you are reversing the reaction for an oxidation reaction, you must also reverse the sign of the potential. I'm sure it's logical to you, but we need to make sure that we write this down. If you're reversing the reaction to show that it's oxidation, you must also reverse the sign of the potential, right? So if the cell potential, for example, for the lithium ion is negative 3.045 for its ability to gain the electron, well, if I now need to lose it, when I reverse the reaction, it's now going to become a positive value, positive 3.045. We'll come back to the chart again as we move through our details of the electrochemical cells. But again, for the time being, what are our takeaways from this chart? Well, first of all, you can find it in the reference packet at Table D. Second of all, every reaction on here is a reduction reaction, but we know that you can't have reduction without oxidation. So once you identify your two species that are in the reaction, you know you're going to have to reverse one of the reactions as they're written on this chart, because it needs to represent oxidation. And when you reverse the reaction, you're going to be reversing the sign. Now, in terms of what species will be reduced or what species will be oxidized, generally speaking, towards the top of the chart is reduced, towards the bottom of the chart is oxidized. The better way to say it is that the more positive E cell value will be reduced and the more negative E cell value will be oxidized. And again, we are reading these values on this chart. It's not after we manipulate, it's by analyzing the data on the chart. So let's try to pull this together. We have seen a chemical reaction such as this written in its net ionic equation form. The copper 2+ ion reacts with solid zinc to produce the zinc ion and solid copper. This would have been the net ionic equation for what we would have called single replacement reaction, but we now know that it's a redox reaction. When you look at the charges, copper's oxidation number is changing from 2+, which is its charge, so it's +2 for the oxidation number, to 0, and zinc's is changing from 0 to +2. Since their oxidation numbers are changing, we know that this is actually the loss or gain of electrons, or redox reactions. Now, we said at the beginning of our lecture that these spontaneous reactions are going to produce electricity. But we've done tons of single replacement reactions in our lab this year that never electrocuted us or created some type of charge on the table. And you're right, when you just allow the chemical reaction to happen, the electricity isn't there per se. It's something that needs to be harnessed. And that's where this picture comes into play. We actually need to separate the two reactions to have reduction take place in one and oxidation take place in the other. And by separating the two half reactions, now we're able to capitalize on those electrons lost and electrons gained and actually harness and use the electricity. So that's why these chemical reactions within electrochemistry are referred to as electrochemical cells. We actually have to build or manipulate the reaction some way so that we're able to harness the electricity, right? We would have just done this simple reaction in a test tube, and we would have seen the blue colored solution turn colorless, and then the zinc, which was originally like a silvery gray metal, would have turned that reddish brownish copper color. So you saw this reaction already, and we didn't have the electricity produced, and it's because we didn't separate the reactions. So that's where the rest of this lesson is going. We are now going to learn about the two different types of electrochemical cells, and we're going to spend today's lecture focusing on this one, the voltaic or galvanic cell. All right. The two types of electrochemical cells are, as I just mentioned a moment ago, voltaic or galvanic, and the second one is the electrolytic. Let's look at their pictures for a second. Notice in the voltaic or galvanic cell, what we're doing here is we have two beakers. In one beaker, we'll have the oxidation reaction, and in the other beaker, we'll have the reduction reaction. And this is the one that's spontaneous. This is the one that is just naturally going to happen. And since it's a spontaneous reaction, just like we wrote down in our opening slide, the chemical energy or the chemical reaction will produce the electrical energy or electricity. Comparing the voltaic or galvanic to the electrolytic, when you look at its image, you'll notice that this is simply taking place in one beaker, And you'll also notice that we have to have a battery. And that's because the electrolytic cell is non-spontaneous. The species that we have in here are not going to readily undergo oxidation or reduction. Humans have to force it to happen. And we're forcing it by taking electricity, which can be found in our battery, and we're forcing the chemical reaction to happen. There are some commonalities between these two types of cells that have to do with new vocabulary words. So the last thing we're going to do with both of the cells is talk about what vocab words are the same. And they are the words electrode and electrolyte. The electrode is a metal, usually in the form of a bar, that conducts electricity between the cell and its surroundings. Let me go back to the picture for a second. In both of the cells, we've got these bars, these metal rods, that collectively are called electrodes. As you look at the labels, you'll see that they are more specific. Let's get down the definition though. Generally speaking, an electrode is the metal bar that conducts electricity between the cell and its surroundings. That would be, for example, an analogy would be like ions, right? That's a particle with a charge. But we know that there are two types of ions. We could have the anion and we could have the cation. Well, an electrode is a metal bar and we can have two of them. See how in the picture we have two metal bars in each of our cells? Well, those metal bars are going to be further categorized as cathode and anode. Cathode and anode. No matter what cell you're talking about, reduction will take place at the cathode and the oxidation reaction will take place at the anode. That fact is just that, a fact. No matter which cell you're looking at, the reduction takes place at the cathode, oxidation takes place at the anode. And when you look at this slide, some of the letters are color-coded. We have red for reduction and cat for cathode. Red cat. That might be an easy way for you to remember that reduction takes place at the cathode. Then in purple, we have ox and an. I know, it's a little bit backwards, but if you think of it as a sentence, an ox, perhaps you'll remember that the anode is where oxidation takes place. So it's like we're at a little zoo when we're dealing with electrochemistry. We've got Leo the lion saying grr, and then we have red cat and an ox. They all have meaning. Red cat, reduction takes place at the cathode, and ox, oxidation takes place at the anode. Now, what won't be the same is that the charges will be different for each cell. So you can't memorize what the charges are going to be, but you can absolutely memorize that reduction will always take place at the metal bar called the cathode, and oxidation will always take place at the metal bar called the anode. The last component that both cells had, right? Both cells had the metal bars. And you'll notice that they also have solutions. And that's what the second component is that they have in common, the electrolytes. Remember, electrolytes are any solution that conducts electricity because it has free-flowing ions. And the electrolyte in electrochemical cells will be a mixture of ions that are involved in the reaction, or their process is to simply carry charge. All right, so now that we've talked and introduced the two types of electrochemical cells, we're now going to spend the rest of today's lecture focusing on the voltaic or the galvanic cell. The next lecture to follow will focus on the electrolytic cell. All right, so here we have a picture of the voltaic or galvanic cell as if it were to be set up in the lab. You can see our two metal bars soaking in two beakers that have electrolytes. We've got a voltmeter here so we can measure the amount of electricity that is being generated as a result of this chemical reaction. And I don't know exactly how well you can see it, but there is this U-shaped thing here connecting the two beakers. That is a very important part of the voltaic cell, which we'll learn about in just a moment. So when you look at the two half reactions, okay, I haven't specified which is which yet because we don't necessarily know what our solutions and metal bars are. In the oxidation half cell, which we know will be called the anode because oxidation will always take place at the anode, we're going to have a metal bar immersed in its own metal ion solution. The metal bar will be the reactant, and it's going to, Leo, the lion, it's going to lose electrons. So that metal bar is going to conduct electrons out of its half cell. Those lost electrons must now be gained, from the reduction. And we know that reduction is always going to take place at the metal bar called the cathode because of red cat. Again, that metal bar will be immersed in its own metal ion solution. The metal bar will be the product, and it's going to get those electrons and conduct it into its half cell. The component that connects the two beakers is called the salt bridge, and we're going to take notes about that in the next slide. To figure out what the relative charges are, well, the electrons are going to flow from the anode where they build up because that's where we're losing electrons in oxidation. If electrons build up, electrons have negative charge. So if those negative charges are building up on the anode is going to be negatively charged. Those negative electrons are then going to get sent to the cathode, where they are depleted, right? Because that's where we have our reduction reaction, where those electrons are gained. If I'm removing negative, that means it must have a positive charge. Let's talk in more detail about the salt bridge. Why is it that we need it? Well, we need to have the common ion from the solutions be able to travel back and forth between them, allowing them to stay neutral. In other words, if I have these electrolyte solutions here, where one of the metal bars is taking the ions out of the solution and turning them into their own, to the metal form, whereas this metal bar is now putting the positive ions back into the solutions themselves are now going to no longer be neutral. So this salt bridge here, the connecting between the two beakers, is saturated with a salt solution, and the ions in the salt are going to migrate into the respective beakers or cells so that the cells stay electrically neutral. This occurs by diffusion. Our salt bridge is going to be having a high concentration of ions, and they're going to go into the beaker where there's a low concentration of ions. And the way that it works is that the anions in the salt bridge are going to migrate towards the anode, and the cations in the salt bridge are going to migrate towards the cathode. And that is not a mistake. Anions go to the anode, cations go to the cathode from the salt bridge. We're not talking about the chemical reaction. So now let's try to put this all together. Okay, let's go back to this voltaic galvanic cell that we saw just a little while ago. And now, even though a lot of the work is done for us, let's start to interpret what's going on. We know that this is our overall reaction. The copper 2 ions, whose oxidation number is +2, are being converted into copper, the element, whose oxidation number is 0. This number is becoming more negative, so my copper is reduced. zinc, its oxidation number is starting out 0, changing to positive 2. That's becoming more positive, so it's oxidized. Just to confirm with you, if you could go to your standard reduction potential chart, let's look up those half reactions. We had the copper 2, excuse me, the copper 2, and then we had zinc. Sorry that my highlighting here is too thick. There are 2 half reactions. According to what we said about the standard reduction potential chart, looking at these 2 E-cell values, the one that's more positive will be reduced, and the one that's more negative will be oxidized. Copper 2 plus, that's more positive. Zinc 2 plus, that one's more negative. Double checking, that's exactly what we said. The copper was being reduced, the zinc was being oxidized. So I just want to share with you how that's matching with our standard reduction potential chart. All right, so now let's look at where this is in our beaker or our setup, our cell here, excuse me. This metal bar here on the left is sort of brownish reddish in color, so I know that that's going to be copper solid. And because that is going to be with the reduction reaction, I know that reduction takes place at the cathode, so I'm able to label the copper metal bar as being the cathode. Now, looking specifically at the copper half reaction, the copper 2 ions are being converted into the copper metal. Where are those copper 2 ions coming from? They're coming from the solution. This bar is resting in a solution of copper 2 sulfate. Copper 2 sulfate's an ionic compound, so we know as soon as it goes into water, those ions are going to be dissolved and free-flowing. These copper 2 ions are gaining electrons, and they're forming solid copper. So as I look at all these the copper 2 plus ions conforming into solid copper, this particular solution here is being depleted of the cations. And that's where our salt bridge comes into play. Because the cations are being taken out of the copper 2 sulfate solution, there's now a buildup of anions in that beaker, and that's not good. We have to keep the solution electrically neutral. So the cation in the salt bridge is now going to migrate in here and start to replenish the lost cationic charge. Hopefully you're going, oh, I get it now, I get it. Now these electrons can't be gained by the copper 2 ion without having a species that's willing to lose it. And that's our oxidation reaction. So let's take a look here. I've got my silvery gray metal bar here, so I know for sure that that's going to be zinc. And I can classify it as the anode because I've already checked on my standard reduction potential chart that the zinc half reaction is going to be the one that's oxidized. So again, how is that working? Well, let's look at the reaction. The solid zinc, or the metal, is going to lose its electrons and turn into the zinc 2 plus ion. And remember, those ions are aqueous. So what's happening here is the metal is losing its electrons, and as a result, it's forming, sorry, it's hard to tell the difference between my Z's and my 2's. It's creating all of these extra cations in the solution. So as a result, I now have too many cations, and the anion from the salt bridge now needs to migrate into the solution to try to balance out the charge. The last thing I want to talk about with charge is what's going on with the metal bars. As you can see, we've got these labels of negative and positive here. The negative is always associated with the anode in a voltaic cell because anode is where oxidation takes place and oxidation is losing electrons. So this bar now has a buildup of negative charge. Hence, it's negative. And again, the way nature works, when you've got too much of something, it's naturally going to migrate to an area where there's fewer of them. So the wire that's here passing through the voltmeter is necessary to conduct the lost electrons to the bar where we want to gain the electrons. And now that once it's, those electrons now travel, and when they get into the solution, those copper 2+ ions are now going to be attracted to those negatives, saying, hey, I want you to come join my electron cloud. And now they're going to wind up forming the element and plating onto this bar, right? Because that's where the solid is going to go. And that's how we harness this single replacement reaction, which we are now calling a redox reaction, to generate electricity. So how is it that you're able to see these voltaic cells? Well, they could just look like a regular, ordinary single replacement reaction, or they could give you these straight up and down lines, right? Where this is sort of like your yield sign or your salt bridge, but they're telling you that this is taking place in one cell, and here's what we've got in the other cell. And how is it that you know? Exactly what we did before. You find the half reactions on the standard reduction potential chart. The one that's more positive is reduced. The one that's more negative is oxidized. And then you should know like how it gets set up. You'll need 2 beakers. You'll need a metal bar in each of the beakers, and that metal bar has to be the metal that's in the reaction. And you'll notice that it's dipped into or dunked into a solution that contains its own metal, but in the ion form. And we need to connect it with a salt bridge. And then you'll connect the metal bars with a wire. And that's always how these voltaic or galvanic cells will be set up. So let's finally end things by working through our own analysis of an electrochemical cell with as little detail as possible. Here we go. So again, I know this is going to be the voltaic or galvanic cell because I've got the salt bridge, I've got a voltmeter, I've got my 2 reactions, half reactions that are going to be separated from each other. I've got a metal bar, I've got lead dipped into a solution that contains its own metal ion. And again, aluminum, the metal, dipped into a solution that contains its own metal ion. And then the first question says, which is more easily oxidized? The aluminum or the lead? Well, that takes us to our standard electron reduction potential chart. We know that the more easily oxidized ones are the ones whose E cell values are more negative. So let's look them up. I've got aluminum going to aluminum 3+, that's its ion. The aluminum 3+ ion. And I know that I've got lead, based on the formula, going to the lead 2 ion. So I'm going to go to my standard reduction potential chart, and I'm going to look for those. I'm looking for the aluminum to aluminum 3+, and I'm looking for the lead to the lead 2+. And I'm going to see where they show up. You can look in your packet. I'm going to look here. found the aluminum one. The lead, the lead, the lead, the lead. It's written much clearer on your standard reduction potential chart. Negative 0.13 on your chart shows us having Pb2 plus 2 electrons to yield Pb solid. So here we have our second half reaction, which will be reduced, which will be oxidized. The one closer to the top is reduced, right? The more positive. The one at the bottom, more negative, will be oxidized. And this is what I was trying to tell you before. Like, we have two species, both of whose cell potentials are negative on this chart, but that's okay. We can still figure out what's reduced and what's oxidized based upon the premise of more positive and more negative. It doesn't have to be, something above hydrogen, something below hydrogen. It's not how the chart works. All right, so now I know which is more readily reduced, what's more readily oxidized. I can answer the question, which is more easily oxidized, the aluminum or the lead? It's the aluminum because it's closer to the bottom. So what's the balanced equation showing the spontaneous reaction that occurs? Well, I know that this is a reduction half reaction chart. So this part here, the lead 2 plus, that one's going to have to stay the way it is. However, my oxidation half reaction is going to need to be switched. So that's going to have to look like aluminum solid gives me aluminum 3 plus 3 electrons. So just as we've been doing with enthalpy, we're just going to kind of add them up. However, perhaps at glance you'll notice that the electrons gained and the electrons lost don't match each other. However, in nature they have to. Our electrons lost have to equal our electrons gained. The number they have in common is 6. So if I multiplied the lead half reaction by 3 and the aluminum half reaction by 2, then I would wind up having the same number of electrons lost and gained. In other words, we would need 3 moles of the lead 2 ion, which would give us 6 electrons, and 2 solid aluminums to give us 3 solid leads, 2 aluminum ions, and 6 electrons lost. The 6 electrons show up on both sides, so they cancel each other out. So I can clean this up by writing 3 Pb2 plus 2 aluminums yields 3 solid leads and 2 aluminum ions. All right, let's recopy that down. Whoops. So when you now look at the overall reaction, we're balanced for mass and charge. Question number 3. What is the maximum voltage that the above cell can produce? We had this fun formula. The E cell is equal to, and we had it all the way back in our beginning slides here. Hope I'm not making you dizzy. The cell potential of the cathode plus the cell potential of the anode. Cell potential of the cathode plus the cell potential of the anode. Red cat, reduction takes place at the cathode. We had said that the lead would be reduced, so the value is negative 0.13 for the reduction. Negative 0.13 volts is our cathode. And oxidation takes place at the anode. The oxidation half reaction was the one that we had to switch. So by switching the reaction, we also have to switch the sign. So it winds up being positive 1.66. So doing our math, 1.66 minus 0.13 volts is positive 1.53 volts. Our E cell is positive, which means it's spontaneous, and that is the truth for all voltaic cells. So you need to make sure that our value is positive for the voltaic cell. Positive 1.53 volts. What is the direction of electron flow in the wire? Well, we needed to figure out where oxidation and reduction takes place. We said that more easily oxidizes aluminum, so here's going to be oxidation. That's our anode. Reduction is going to take place here on the right. That's the cathode. The electrons are going to have to naturally flow from where they build up or get lost to where they are going to be gained. So that's the flow of the electrons through the wire. They flow from the anode which in this case is the aluminum, to the cathode. Which in this case is the lead. So key note, we were in the wire. We always go from the anode to the cathode. The next question, number 5, asks, what's the direction of the positive ion flow in the salt bridge? Right, so in the salt bridge, in here, we have different chemicals that have cations and anions in them. And we are going to ask the positive ion flow, that would be the cation. The cations in the salt bridge, you can either memorize it or you can logically figure it out. The cations need to deplete the cations that are being lost from the solution. So when I look at my chemical reaction, the cations that are getting used up are my lead. So the cations from the salt bridge are going to have to replace the cations that are reacting, which is in the cathode half reaction. So for those of you who want to memorize, the cation from the salt bridge goes to the cathode, go for it. For those of you who want to logically deduce it, that's fine too. You'll get to the same answer regardless. So the positive ions in the salt bridge are going to the cathode. Which is the lead. Which electrode is decreasing in size? Versus number 7, which electrode is increasing in size? Electrode is our vocabulary word for the metal bar. So one of our metal bars is getting smaller and the other metal bar is getting bigger. Well, even if I've managed to confuse you unknowingly as of right now, we can always look back at our chemical reaction and answer it, right? The electrode that's decreasing in size is the one where the metal must be a reactant because it's being used up. And the electrode that's increasing in size must be the metal that's being produced because it's being made. So the electrode that is decreasing in size will be our aluminum. It is a reactant. It's being used up so that we can get the lead ions out of the solution to make the element lead on the product side. What is happening in number 8 to the concentration of the aluminum ions? Well, let's look at them. Again, you don't have to look at the cells if you don't want to. Just look at the chemical reaction. What's happening to the amount of the aluminum ions? Well, here they are. The aluminum ions are on the product side. So what must be happening to their concentration? It must be going up. They're being produced. What's happening to the concentration of the lead ions? Again, let's find it. Where are the lead ions in our reaction? Here they are. They're on the reactant side. They're being used up. So what's happening to their concentration? They're decreasing. A connection question. What is the voltage in the cell when the reaction reaches equilibrium? Well, equilibrium means the rate at which the forward reaction or the reactants are making products and the rate at which the products are making reactants will be the same. When the reaction first starts, our voltage is going to be 1.53 volts. That's it's going to be maximum. And what do we suppose will happen when the reaction reaches equilibrium? Well, this number is slowly going to start to go down, 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 until it reaches the state of 0. When your voltage is 0, it means that your redox reaction no longer has electrons to lose and electrons to gain. Real-world connection, my friends. This voltaic cell is what exists in your batteries. When your batteries die, there are no more electrons lost and electrons gained. In other words, your voltage has reached 0. Technology and scientists over the year have started to create rechargeable batteries. By plugging your battery back into a socket, you are now reversing the reaction. You're now using electricity to produce the chemical changes. So you are replenishing the lost electrons, and then when you unplug the rechargeable battery and now start to use it again, it's naturally going to discharge. Isn't it so exciting? Yeah. I so wish we were together so that we could do all these labs and work through this together. It's definitely not easy just via lecture. All right, some more vocabulary words. Which is the anode? And ox. Oxidation takes place at the anode. We had said that the aluminum was our oxidation half reaction, so the anode must be the metal form, right? Because the electrodes are the metals, so it's aluminum. What is the cathode? Red cat. Reduction takes place at the cathode. We said that the lead was going to be reduced, so the lead metal, I was about to write PB, sorry. The lead is our cathode. What's the positive electrode and what's the negative electrode? Again, electrodes are our metal bars. I always like to go with the negative one first because I like to think this out logically. The negative electrode is the one where the electrons are going to build up because they're being lost. Lost electrons is oxidation. The oxidation takes place at the anode, so aluminum is going to be my negatively charged electrode, and by default, my other electrode needs to be positive. So here is where we're stopping for today. This was a ton of information. Thank you so much for listening to it. I hope we went at a pace that was manageable for you. You now have an opportunity to do some practice problems by completing the homework that's dropped into our Google Classroom, and I look forward to meeting with you to answer any questions that you may have. In our next lecture, we'll talk about the second type of cell, the electrolytic cell, in as much detail as we did with our voltaic